Okay, please welcome Paul Van Albel, a PhD student at Rabat University in Nijmegen. And he's going to give a talk of physically unclonable functions. A warm round of applause, please. Thank you.
Thank you. Thank you for having me. Thank you for having me on prime time when everybody's finally awake but not yet drunk. And thank you for letting me compete with the space track. My herald doesn't explain who I am, but the work in this talk is actually mostly not from me. It's by many, many authors, and there will be citations on almost every slide. Don't pay attention to those. It was simply too hard for me to make two different set of slides. Download the slides afterwards. If something interests you, the entire intent of this talk is to get you interested in this material, get you reading the papers, and get you implementing this stuff yourself. So without further ado, and without any further ecocentric blathering, let's look at the problem we're trying to solve. In computer security, since the 1980s, we've noticed that we might want unique identification and authentication of devices, and then specifically integrated circuits. So we want to distinguish chips uniquely from the same manufacturing masks even, and with high accuracy, unforgeably. Simple task, right? So in order to explain how we get to physically unclonable functions, I'm first going to explain some history in anti-counterfeiting. And anti-counterfeiting, you can think of money, you can think of magstripe cards, you can think of identity documents, and nuke counters, or as they are commonly called in literature, treaty-limited item identifiers. So let's start with money. Historically, money has been protected with highly intricate imagery. This is an example from right after the US Revolution, and I personally really liked, the to counterfeit is death. Because, well, it was a crime against the state, you were drawn and quartered when you did it. Then we fast forward a few centuries, and I would like to know from the audience who has ever seen this. Quite a lot. Can anybody tell me what it is? The Orion constellation. It's intended to prevent photocopiers from copying your money. So basically, when the photocopier detects this thing, it'll just it will just say, I don't want to copy. You can actually use this on your own stuff if you want. But we see a common theme in those entire few centuries, namely you mark all valid bills the same, and then you make sure that you can check the marks in order to identify that it's legitimate. An alternative to this would be to have different marks for each bill and then sign that marking. But you get into a whole bunch of questions like, how do I then prevent somebody from copying that bill-specific valid mark 100,000 times and just copying the signature as well? It's not as though anybody is checking paper money online. So back in 1983, Bauder proposed an anti-counterfeiting measure, which basically meant you sprinkle random length cuts of optical fibers into your paper before it becomes paper, the mull, and then you make the money and you use basically a light bar scan, so whatever a photocopier does as well, and then there will be a dot pattern that appears around the light bar. And you extract that dot pattern, you make that into a series of bits, and you sign that dot pattern. And then you print the signature onto the bill. Now, there's several problems with this, which are all explained in those papers. I don't have the time to go into that, but in principle, this works. Then next, cards. you know, magnetic stripes and pin, the way we used to use them in Europe. I think you still use them in the US, I'm not sure. Because nobody knows how to copy mag stripes, right? So you add stuff to the card so that it becomes detectable when somebody has copied the card onto a forgery. So do you use holograms? As far as I know, holograms are also copyable now. I don't have the literature reference there, but stuff can be done. Now somebody in 1980 already proposed this. You randomly disperse magnetic fibers in a coating. You scan those fibers with a, well, electromagnetic sensing device and turn them into pulses and pulses with clock, etc. Turn them into bits again, sign that pattern, etc. Then there's also this nice proposal where you randomly disperse conductive particles in insulating material, scan with a microwave. It's basically the same principle from also the 1980s. And next, identity documents. Somebody proposed using the translucency of a paper strip in an identity document, scan that strip, turn the translucency pattern into a bit mask, sign a bit mask, etc. Now, Simmons already said that this was too easily clonable because, you know, you can just take a photograph of this and reproduce it through photographic techniques. So translucency isn't really nice. Now, you could also potentially use the exact three-dimensional cotton fiber pattern of the paper. But that proposal was also in 1991. Simmons also said this is infeasible to do. However, in 1999, somebody came up with something similar. They take the texture hash of a postal envelope. So you just print a square on the envelope, take a high resolution picture of that, and then hash that with a certain hashing code that ensures that all these things collapse into the same bit pattern every time. This works. Then finally, those treaty limited items, the reflective particle tags. You basically affix such a tag to the surface of a treaty limited item. Then you cure them with ultraviolet light so that you turn it into a glass-like substance, which makes it tamper evident. If I try to take it off, the glass breaks. And it also preserves the particle orientation. And then you put a laser onto it, you look at the reflective pattern, and you have your identifier. So if you ever have a bunch of nukes to count, that might be interesting. The common theme here is that we are using an intrinsic aspect of an item that's infeasible to copy, but easily readable. It's unpredictable, and it should ideally be unchanging. Which brings us to a proposal in 2001 of physical one-way functions. Basically, the idea was you have an epoxy with minuscule glass spheres. You cure that epoxy, you make it into a 10 by 10 by 2.5 millimeters, I don't know the exact dimensions anymore. I say sphere, I mean, what's it called? Cuboid? Something like that. And then you illuminate it by laser. And then you get a speckle pattern out of that, because the laser will disperse in a really unpredictable pattern. And you capture that at 320 by 240 pixels. You turn that into a 2400-bit key with a so-called Gabo transform. I have no idea how the math behind that works, because that's not my field of expertise. You get interesting properties like drilling a hole here causes half the bits to flip, so it's tamper resistant, and it mirrors the way one-way functions work, like SHA-1 and SHA-256. Ideally, if you flip one bit in your input, half your output bits should flip. So this paper is really the first paper that proposed this as a connection with cryptography. So here, reading the structure is feasible because you have this glass pattern. You can just, well, I say just, but you can use microscopic techniques to read it out exactly. But good luck with having this submicron accuracy for all those glass spheres in the epoxy. You can, in theory, if you know the structure, emulate or simulate how a laser passes through this, but it requires a lot of computational power. And in order to, you also can't build a database of responses to challenges, because imagine that the challenge to this structure is a laser at different orientations, like I can say laser under an angle of 5 degrees or 10 degrees or 20 degrees, and at different locations. And all those responses will be different. So this challenge response space is infeasibly huge. So the protocol here would be, first, you read this thing on a trusted terminal, and you create a random collection of challenge response pairs. Your challenges have to be kept secret, because next you get an authentication request from an untrusted terminal, and you challenge that terminal. And the idea would be that it's infeasible to send the correct response key if you don't have the device containing this PUF, this physical one-way function. So you then receive the response key, and you reject this if the key differs by too many bits, because it won't be a perfect match. I mean, there might be scratches, there might be slight micron differences in the orientations, it might be a bad camera, you get some differences, and the way you then do this is you calculate the least probable acceptance rate of a counterfeit device that you want, and then you get to this amount of bits. And then you can get a better match rate if you repeat steps 4 through 6 a few times, and if you run out of challenge pairs, you could just go back to 1. That's the general idea. So this is the first paper that made this connection with cryptography. It has a defined protocol, but there are several not so nice things, like you have special equipment required, and we would really like to have the same possibility in silicon and silicon only. Now, in this paper already, the proposal was that you might be able to have a similar approach if you scatter electrons, I don't understand what this says, but I know that is not what we're going to see next. So, as an aside, if you do this kind of thing, then you get to read very old papers. So, wasn't it nice back when you could say this? In the fuel rod placement monitor, high radiation levels in the hot cell provided the general tamper resistance. Or the seismic sensors would detect any attempt to gain physical access to the package long before the information security is in jeopardy. Now, I wouldn't actually take that one as a bet because I know you guys, but the first one is pretty good. And you get to see things like this. This is how RSA was done in 1984. This is I think that's an ESA, maybe pre-ESA bus, I don't know. So this is how that was done, and the text is really beautiful. They scanned an old, basically typeset on a typing machine paper. This is available online, by the way, if you have university access. Sorry. Then there are other solutions to this problem. Of course, you have hardware security models, you have smart cards, you have trusted platform modules. Actually, I found out we only have those since 2006. I thought they were older. But you still have the problem of key management, right? Because the key isn't tied to the platform. If I can extract a key and put it into another trusted platform module or another hardware security module, then we're still dead in the water. So the aspects of these things is the key never leaves the device, ideally. But then how does the key enter the device? You can enter new keys. You can enter key encrypting keys to decrypt keys that you never see, etc. Then another hardware security module exports. It's all Interesting crypto, but you also get the problem of what can the key do? Are you limited to 1024-bit RSA? And is it possible to emulate all this once you have the key? Right? We really want to have other aspects to our function. Now, this is the first name for PUFs. Silicon physical random functions, but they already knew that PRF might have some three-letter acronym clashes with pseudo-random functions, so they decided to go for physical unclonable functions. There's an interesting discussion going on whether it should be physical or physically. Not going into that. So the idea is tamper resistance in general is expensive, is difficult. It's just, let's look at a different approach. There is enough process variation across identical integrated circuits where, so they're not identical because of those process variations. And already in 2000, somebody made, Lawson, Dash, and Taylor had a small paper on specific, special device identification circuits. But if you want to use those for secure device identification and authentication, then just a single such circuit is not enough. You need more. So what do? You build this, and I don't think it's really visible, but basically this is the entire circuit. You have a delay circuit here. This is a ring oscillator PUF. So you have a delay circuit here. This is a self-oscillating loop. Basically, this feeds back into this. And the challenge here is a bit for each of these blocks. And what the bit says, if it's 1, then you pass through. If it's 0, you pass over. So if you have a different challenge, you have a different path through this PUF. So ideally, for each challenge, it should be unpredictable whether this final arbiter block here, somewhere over there, gives a 1 or a 0, and then you count the pulses, and you identify your circuit. Now, attacks on this were also quite well studied as possible attacks. So you have the duplication attack, which is basically cloning, which should be impossible. Right? That's the general idea. Cloning should be impossible. There is emulation from measuring. So you build a model from this by measuring the exact distances between logical units inside a PUF or the length of the wires inside a PUF. Also deemed infeasible because how are you going to measure this without destroying the PUF? This is back in 2001. Then there was emulation for modeling. So basically, if you get these challenge response pairs, if you get enough of them, you can apply some nice machine learning algorithms to that, and then you get prediction of responses. And finally, you have the control algorithm attack, which is attacking the PUF's control algorithm without ever getting into the PUF. If you can do that, then your PUF is useless. So they also proposed controlled physically unclonable functions, which is the same but with bells on. So you have an access function for the PUF, which is part of the PUF. This is to prevent against that that final attack. So basically, where you overlay the logic of the access function with the PUF, so that to access the logic of the access function, you have to break the PUF. And if you break the PUF, everything breaks, no longer works. So this gives additional properties. An uncontrolled PUF can only be used for device authentication. This can be used to have nice things like proof of execution on a specific device, potentially things that I don't have an opinion on code that only runs on specific devices. But basically, whatever you need a secure cryptographic key for, you should really be using a controlled PUF, is the idea. But you can still do device identification. So how does a controlled PUF look? You have a random hash here, you have a potential ID here, you have the PUF here. So challenge, ID, personality into the random hash. You run it through the PUF, do some error correction because PUFs are not ideal, and then the random hash again, and then the response. This is to prevent all these attacks. If you're interested in this, read the paper. Then in 2011, a formal model was proposed. What do we really need from PUFs? First, we need robustness. Across evaluations, we need the same response. We need physical unclonability. It really shouldn't be possible to clone these things. And we need unpredictability. Now, these two are potentially at odds. So we'll get into that at the final slide, I think. And since then, since 2001, there have been a lot of proposals and attacks on PUFs. So first, there are the arbiter PUFs, which are all delay-based. So the general idea here is that if you run a signal through a chip, it's delayed by a certain amount. But the amount is unique per chip. But it turns out that you can pretty easily model this. And even the bistable ring PUF, which is fairly recent, I think, you can do some fancy machine learning. I would highly recommend this paper, PUC learning of arbiter PUFs. Basically, the idea is you have 30,000 challenge response pairs, and that's enough to give you 100% accuracy on a 256-bit challenge PUF. That's not good. This doesn't really work if you can model it that way. And you can also use optical measuring of signals through devices at 6 picosecond accuracy. So these things might not be around for much longer. Then there are memory-based PUFs. They are based on bistable memory, which basically looks like this. And it's also delay-based, but here it's unique to this cell. You have a block of these cells. They are all independent, so you get a pattern out of this. These cells go to 1 or 0, and they are pretty fairly stable in doing this. I'll show you a picture later of what happens if you have a nice PUF of this type and if you don't have a nice PUF of this type. However, if you have a SRAM PUF, for instance, you have fairly limited SRAM. So you can just, in principle, read all this out and store all the bits in a database. And then you can clone the PUF because you can use focused ion beams to trim the SRAM of another chip into the correct orientation. And, well, emulation, if you have this database, you can just respond from your database. So this is, in some literature, termed a weak PUF, but it's probably still the most useful one we have right now. This is usually also what's in your devices if it's claimed to have a physically unclonable function, but they are of the controlled variety most of the time. Then finally, recently, somebody proposed, I think that was, Shalaksung and Anagnostup, cannot pronounce that. But the decay-based PUFs, the idea is you have DRAM, take the power off, put the power back on, look how it decayed. No attacks on that I have seen yet. So the final few minutes of this talk will be about your very own memory PUFs, which is trivial, right? No, it's not actually. And all this time before, you might think, why would we even bother with this? It seems to be hopeless for PUFs. There is not enough randomness in the silicon, but I disagree. Because for one, some protection is better than none, which is what most system-on-chip devices have. And two, I do not believe in silver bullets. This should be part of a greater security mechanism. So if nothing else, if all you want from this talk is some interesting paper to read, just one, read this one. That's on slide 39. It's called Lightweight Anti-Counterfeiting Solution for Low-End Commodity Hardware Using Inherent PUFs. And preferably you also read this related one, PUF-based software protection for low-end embedded devices. Don't be fooled by the terms IP protection and license model. This is a secure boot environment. You want it in your Raspberry Pi, for instance. I don't know whether Raspberry Pis have it. That's for you to find out. So what you'll need is a device with a masked ROM to hold the bootloader. Like the first stage of code needs to be under your control. You need to have that modifiable startup code. You need to be able to modify it, obviously. and you need onboard SRAM to build the PUF on. And then you need some non-volatile memory for encrypted firmware and helper data. So in the Puffin project, which that earlier paper was a result of, there are several results here. This is an STM32F100B microcontroller. This is a Panda board, which is pretty much like a mobile phone, actually. So what you want to see is this, white noise. This part is a PUF-like memory range. This part is probably spoiled by the bootloader or something like that, or the ROM code. But this you can use. This looks good. So once you have such a white noise area, you start measuring a lot of times, and then you compute the Hamming distance between lots of measurements from lots of different devices. And you want it to look like this. You want it to be around half, because that means that every device will look different by about 50%. You also measure the inner class Hamming distance, which is same measurements from the same PUF, and you want that to be below 0.1. You don't want that to be too inaccurate, because then your error correction becomes too complex and starts leaking information. And you will need error correction using, for example, Golang codes. So this first paper I mentioned, this one, lightweight and counterfeiting one, this is also from that paper. Read it. It also explains how this fuzzy extractor works. If you're interested in this, there's lots of scientific literature out there. And then finally, you build this fuzzy extractor, and then you enroll your chip, and you generate some helper data for this error correction. And then once you challenge the chip, you send this error correcting data with the challenge. And in the end, the idea would be that you get a secret S prime from every chip. Now, how can you use this? You have the bootloader and the master ROM. This is the first stage bootloader. It challenges the PUF and decrypts the second stage bootloader, which comes from external memory. And then you boot the embedded operating system. This should look familiar to a lot of you, because this is basically also how device attestation on x86 works if you're using trusted platform modules. So in a bit more detail, same procedure, create a PUF, decrypt and call. Here the key also ends up, and you decrypt and call the kernel. And then finally, this is how it really looks in real detail. And even if you don't want to build this, you'll still have this. So remember when I showed you the inner class Hamming distance? The 10% of differences between measurements? That's caused by the red dots. Those are the unstable SRAM cells. You can use those as seeds for a random function. And hopefully you won't have this. This looks wrong. This is not a PUF. This is too predictable. Unfortunately, all this won't be possible on x86, because we looked for the PUFs in the CPUs, but Intel and AMD both explicitly zero everything. Finally, a word on privacy. I don't have too much time for this, but I really like the fact that they mentioned they feel that users feel that they can be tracked if you have a unique identifier, as though it's not a valid concern than the users being paranoid. Now, back to the controlled PUF. You can add personality IDs as a user. If you challenge it, you add a personality. So one application reading the PUF gets a different ID from another application, which changes the entire output of the hash function. No paranoia required anymore, hopefully. Finally, the references. Google Scholar is your friend. The rest of the slides are all kinds of references. Read it. You've already seen all of those. Read it. Thank you for your attention.
One question.
Thank you, Paul. We have time for maybe 2 questions. Please come up to the mics. Mic 3.
What do you think about MEMS-based physical unclonable functions, where they basically use the accelerometer sensors and the deviations in these sensors by inducing challenges as controlled vibration?
Sorry, I missed the first word of your question.
The MEMS-based, basically the technology that is being used to build accelerometers in silicon. So Bosch has some PUF chips based on that, where they have arrays of these MEMS chips and then a controlled vibrator to induce the challenge into that.
I think they're probably more secure than silicon-based PUFs because they are built for randomness, whereas we're here trying to extract randomness from an existing circuit. Yeah, they're interesting. Use them if you can, but most people don't have the option.
Thank you. More questions?
Up there?
Okay, Mike 7.
Hi, thanks for your talk. I'd never heard of PUFs. I recently went on a quest to find a usable smart card that met all the things I wanted to do, like open source, etc. Can you expand a bit on how PUFs could be used with like an OpenPGP smart card or similar?
Short answer, no. I have no idea whether OpenPGP will ever support anything like this. You have the PKCS protocols. I know that in theory this is possible. I don't know whether anything has implemented it. There are PUFs on smart cards, but whether we haven't looked into this. I don't know of anyone who has.
Thank you.
But that doesn't mean it doesn't exist.
That would be all. Please give it up for Paul one more time.
Thanks.